Nice. चलो final week, final नहीं final week, final session. Oh god, 2 months है. चलो silent हो जा. एक मिनट बताओ. Just a minute. Hello. Sorry, I'm not in Bangalore right now. Right. Let me put it in. Sorry. Okay. I'll trim up this part from the video. Chalo. Anyway, so let's go and let's start. Okay. So the first. Okay. Am I audible? Just confirming because there was a.
Yes.
Right. Chalo. Nice. Recording is also audible. Chalo. Let's jump in. So in this one, so the first one that we'll tackle is like obviously geo is something that we have seen a lot of growth around hyperlocal delivery. Like Swiggy came, Zomato came, Uber, Ola, Shadowfax, right? Like so many companies operating at geo. The biggest app, the most widely used application, geo, cars, Google Maps, location-based reminders, Go and whatnot. Like so many things came up once Google Maps revolutionized the entire geo sort of thing, basically everything which was geocentric, it became quite evident that people became very innovative with the kind of things that they could do, having a location of a user. For example, location-based theming and whatnot. Okay, so Facebook nearby friends, there are so many things that has sprung up because of that. So it obviously made sense कि चलो we should also talk about geo based stuff, any sort of specific application to strengthen our understanding of this part of ecosystem which deals with location, lat long and geo coordinates. So in this one, what we'll talk about is we'll take one example as something as a centroid to this problem, and then we'll talk about various things that we can do with this part. So there is this very famous algorithm called geohash. What it does is it helps us give, no, it basically gives us people who are nearby to us. Like for example, when we talk about like system design of Tinder, like something around that line. People talk about database design. People talk about like ठीक है कुछ high level architecture, multi availability zone and stuff. But that's not a challenge for Tinder. Like even मतलब even after going through like six weeks of this coursework, you could very easily design a database schema for it, or you can see how it scales, how to partition, how to shard, all of those parts. The core challenge when someone talks about Tinder, the core challenge is not scaling things up by doing sharding and doing multi-availability zone. That's a very dabba drawing system kind of stuff. Okay, but the most important or the biggest challenge that Tinder had was to find out people near you. Like when we talk about Tinder, it's all about like I'm at a pub, I'm dancing to some tune, and I'm like, chalo, let's hook up, and you open up Tinder, and then it shows you people who are near to you, right? Basically geographically near to you. Like that is something. If this wouldn't have been there, Tinder basically Tinder would not even have existed, right? Because this is the core problem that Tinder has to solve, and not some like scaling problem by partitioning and sharding and those kind of stuff. This is the fundamental thing that Tinder had to solve, or Tinder required the tools that solve this problem for it to exist. Otherwise, obviously, Tinder wouldn't exist. Now, uh, okay, if this is the biggest problem for Tinder, what's the second biggest problem for Tinder? I might have already spilled the beans, but yeah, let's see how many of you recall. What is the second biggest problem for Tinder?
As in, if you have swiped or not, like already.
Yes, exactly. Like it's like the person who I've already swiped either left or right, I should not be seeing them again on my profile. This is the second biggest problem of Tinder because database schema again, database schema scaling is all okay, but this is a very important thing because this has to be done efficiently and at scale. Okay, so people who I have already seen, as in who I have already either swiped left or right, I should not be seeing them again, even though they are sitting right on the next table to me. I should not be seeing them on my Tinder while I am doing a left swipe, right swipe sort of stuff. Okay. Before coming to the first problem, how will you solve the second problem? To not show people who you have already swiped.
हमने bloom filters decide किया था.
Exactly. Bloom filters is the best way to do it, right? Because it's the exact same, it sits on that exact same thing. I've read an article, I've swiped the person, so now it gets ingrained in your head. Okay, whenever you are making a decision, something that I've already consumed, I don't want to consume it again, the answer is Bloom filter. Okay. So that's the second biggest problem of Tinder. Now coming back to the first one about finding out people who are closest to you within K kilometer of radius. Okay. This is the core problem statement. And how will you solve it? Okay. Assume you guys don't know about geohash. We'll first set up why do you need a separate algorithm if you can do this with normal maths, and then we'll come to the solution. Okay. Why do you think it's very hard for us to figure out who are near to us? Anything that you can add here?
Because that can keep on changing over time. Like,
No, let's say that is even static. Let's say all the people in the world, they are not moving for 1 hour, they are all sitting at the same place. Now what? How will you find out people who are closer to you, who are within K kilometer radius to you?
Yeah, so I'll have my GPS location, right?
Hmm.
So and the other user will also have their GPS location, right?
Hmm.
So it'll be one-to-one distance mapping. I mean, for this user, let's say boys and girls, right? If a boy is interested in all the girls, so for all the boys, what is the distance for all the girls, right? And
It's n square then.
yeah, it's n square. It will be very slow. So this is a naive approach, and yeah, brute force approach, which will be very time consuming. But yeah, for starters, if we have a small data set, then we can start with this, right?
So in a two-dimensional space, why is this a very, very big problem? As basically very well put by Vishal, it's a n square problem. Because unless you go through all of them, like if you have done some basic machine learning in which you have done something like the k-means clustering, even in that you'd have to go through all the data points to find out which classes are near to my data point, and then you would pick that to be part of your circle, or basically to be part of your cluster, right? So this is exactly that. So on a two-dimensional plane, unless you go through all the points, you can never know which points are actually closer to you, right? Now just imagine operating at scale of million people actively opening Tinder, hoping to get hooked, and you making that for each person you're going through all of them. Okay. You can then talk about like applying heuristics. Let's say instead of doing it at a global level, let me just restrict it to a country wise. Okay. You might have somehow you would have that way key, let me still do it there. But even on a good night, you might still have to do for a million. Like let's say Bangalore Koramangala ke par mein baithe, you would still have to do that. So million people pe to scan jayega hi jayega. So that is a very inefficient way to do it, because this limitation is mathematical limitation. You cannot efficiently compute the nearness of point to basically from a given point. You cannot do it efficiently. If it was a single dimensional thing, it was very easy, because single dimensional thing matlab everything just sits on the line, and you can very easily find out who are near you within that range, right? Because because line hai, oh sorry, it's a highlighter. Because with one dimensional thing, what would happen is, let's say you would always know that, let's say you are at point 9, right? And then there are, let's say you defined a radius of k. Okay, to find nearness of it, you can keep this thing sorted very easily. You can keep this thing sorted and then just find out who are within that range, right? And obviously you can use binary search tree to store this kind of relationship, and on the leaf node you would have all of these data points which are kept sorted, so something like a B plus tree. Okay, you can make range queries using segment trees. Like, so segment trees, range queries, these are all very efficient data structures through which you can very easily find out range of a certain element, right? So any data structure that gives you good or very efficient range queries is you can use to solve this problem on a one-dimensional scale. But when things become two-dimensional, we suddenly are stuck because we have to go for a brute force approach. This is where a specialized algorithm like GeoHash, it's not an algorithm, it's a data representation technique. GeoHash can come in very handy. Okay. So what do we do? Like see, these are some heuristics that we can apply. So instead of like just now what I was talking about, so instead of comparing with all the people of the world, we just reduce the scope for our brute force comparison, right? So instead of doing at world level, let's do it at continent level, or country, or maybe state or city, or maybe within that one small sub region, and then maybe block phase or lane wise. Like, but doing this for all people, basically tagging people to this sort of stuff is again an immensely difficult problem. So heuristics to some extent might work, but definitely not a scalable solution, and obviously not something that would give a good user experience on a busy Friday night. Okay, so this is not a good choice here. Okay, so tagging at such a granularity is not possible, definitely not at scale, because obviously here we are still assuming that people are not moving, but in real world people are moving here and there, and location would change. People would move from one block to another block, and then your database needs to be altered and then computed and whatnot, and re-tagged rather. It's a heavily cumbersome problem. So that's why doing this sort of stuff, heuristics maybe at country level or a city level might still be okay. But within that, when millions of people are active at the same time, you'd still have to go through like finding those things again, or basically going through those again. That's not easy. Okay. So that's how this now basically, now that we understood why is this like a very big problem, the way we would approach the solution is something very simple. Like, what is that one information that is not changing at all? Okay, that is not changing at all, basically, which like not changing at all with respect to reducing the scope, like tagging them with like Asia, India, Kormangla, Bangalore, Karnataka type sort of stuff. That will keep changing, because if user moves from one place to another place, this would keep changing. But lat long is that one uniform information that we have. Basically, now it has become very common that our first intuition goes towards GPS, but it was not about, let's say, 8 years, 10 years back. Like GPS, itra heavily used nahi hota tha. Google Map revolutionized everything. But now that we think about it, that we have lat long, which is a pure XY coordinate representation of any point on the world, it becomes very easy for us to do it. So that is something that is not changing, or matlab, people moving, but the representation is not changing, right? I'm not talking about value, but the representation of it. So we can leverage that. Okay. So the core idea behind GeoHash is divide and conquer. Okay. So what do we do is, let's say we have this rectangle as a world. Our entire world is this rectangle. And what we do is we always divide it in half. Okay. And we see if it is on left, it is 0. If it is on right, it is 1. If it is on top, it is 0. If it is on bottom, it is 1. Okay. So given this as my entire world, I'm first splitting it in half, basically a vertical split mara. So anything that would lie on the left, anything that would lie on the left hand side. So let's say I'm finding out location for this this purple point. Okay, for this purple point, we are finding the representation of it. Okay, so the idea is divide and conquer. So first vertical split, this is 0, this is 1. Okay. So my first I would write is like my point lies on the right hand side. So I'd have 1 here. Then since it is on the right hand side, I'll make a horizontal cut on it and I'll find key if it is on top or on bottom. If it was on top, it would have been 0. If it was on bottom, it would be 1. It is on top, so 0. Okay. Now we are talking about this rectangle. Now here we would make a vertical split and we'll see if it is on the left or the right. I made a vertical split. It's on the left. Left is 0. So I'll make 1 0 again. Now we have changed our scope to this part. Now we'll make a horizontal cut. When you are making horizontal cut, we'll see if it's on top or on the bottom. It's on the bottom part. If it's on the bottom, it means 1. Okay. Then a vertical cut. Is it on the left or on the right? It is on the right hand side. So again a 1. And I'll make a horizontal cut. If it's on the top or the bottom, it's on the top. Right. We can continuously do this. If you see, this is what we are doing. For any given point, we are constantly breaking our world into half, depending on where the point lies in. We are then basically trying to narrow down our scope. Okay, and we can do this to as much of depth as we need. Okay, we stopped at after 6 iterations we stopped. Okay, you can go till 32. You can go till 32 bits. Let's say our integer size is 32, so we can go till 32 splits like this, and then we can narrowly pinpoint a particular point. And at 32, it's per square millimeter or something, which is like extremely small space you can craft, or you can denote using 132-bit integer representation of it. Okay, so this is what the idea is. So now what would happen through this is, if you see this point, let's just do this part. Okay. Now up till now we have established this point. Let's say we are again trying to remap this. Now what you should be doing is you should keep a very close eye on what the prefix is. So if it was on the left side, it was 0. If it was on the right side, it was 1. Okay. If it was on the top, then 0, bottom to 1. So now when I'm doing this, we know that our point, matlab iske pehle we worked it out and we found out it is 1 0 0 1 1 0. It is basically pinpointing this entire location. So now what actually happens is, if we keep a very close eye on the prefix of it, we see that all the points that would lie on the right half of the world will always start with 1. Remember, now if I make a horizontal split over here and I say this as 0, this as 1. Okay. So all the points that would lie in this part of the world will all start with a 1 and a 0. Correct. So this is how, using the normal bit representation, we are actually defining nearness of it. So points that are closer to each other will have a very similar or very similar prefix. For example, all the points that lie on the right half of the world, they'll all start with 1. Right. So all the points that are here, they'll all start with 1. All the points that are here, they'll all start with a 0. Okay. Similarly, all the points that are here will start with a 1 0, and all the points that are here will start with 1 1. So looking at the prefix, you know that are these points near or not. Okay. So this is what the beauty of this representation is. So this would like give you a very good idea around how we are trying to define nearness using a normal bit representation of a location, in which the heuristic is, if the prefix is similar, the points are near. Make sense? Yes, no?
Yes, yes.
Right? Chalo. Any question till this point? एक आना चाहिए.
You can split by left or right. I mean, how do you, like 1 0 can also be if you horizontally split.
So you can define if you would want to split it vertically, horizontally. But basically, this is what the idea is. So the way you would want to do it, you can pick however you would want to split it. So like you can start with splitting it horizontally at first and then vertically. You can do that.
So online, what would be the score?
Online is it?
Right in the middle.
अच्छा यहाँ पे? This one?
Yeah.
अच्छा उस पे अरे तो the point could be inclusive of one place ना?
अच्छा
Like,
वैसे.
हाँ मतलब it's not mutual. So the point that would lie over here, you can have that basically this. So like this similar to what you do it like I less than equal to. So
Got
you
it.
define this now. You
Got
can
it.
either define this or define this. So first is inclusive, right one is exclusive.
तो ये अभी solve हो गया ना? कि
अच्छा,
now
हो गया ना?
find all
नहीं
the people which are having 1 0 0 1
Zero.
हाँ, but
They are
what
all
data
closer
structure
to
would
each
you
other.
use?
star.
What data structure would you use to find the nearness वाला part?
हाँ, आएगा आएगा.
Maybe is it too early to? हाँ.
Yeah. But यहाँ पे one catch is there. What's that? One edge case. How about these 2 points? And these 2 points near. But with our representation, it would see that the left one starts with 0, the right one will start with 1. It would see that these points are too far away from each other. Correct? Right. So obviously, you cannot get best of all the worlds always. Like so, there would be edge cases that you might have to give up on, but it would give you a very good quick estimate, or it would solve for 80, basically 80-20 rule. With this 20% of very simple looking representation, you will solve 80% of the problems. Bacha 20% chhod do. If you need that accurate to be of a system, then go for a brute force-ish approach. Okay, so you can pick and choose your battle, but there are ways to tackle this problem. We are talking about like basically building that heuristic just say we are able to solve this problem. Now, given this sort of representation, although we are talking in terms of geolocation, this sort of bit level representation of nearness, you'll find plethora of applications around it. You go to Google Scholar and search for geo bit representation. There are so many papers that use very similar representation to this, and they talk about like how they have solved the nearness problem in 2-dimensional space, not just for geolocation, but for so many different problems. So a lot of data science algorithms, they actually leverage this sort of geography and use this sort of optimization to make their algorithms faster. So there are so many applications around it, but the core idea remains the same. Okay, you continuously try to divide and conquer and just use then you can just use a common prefix to find the corner. So now job becomes very simple. If we can very efficiently do prefix matching or longest prefix matching efficiently, that would like okay, we'll get everyone who is near to us in one shot. A great part of this approach is, if you see, once you move towards the right part, you are basically zooming in, right? You are making things more and more you are basically increasing the granularity of it. Okay, at what level can you at what level are you able to represent your information? Like if I do it like basically continuously again and again, splitting it horizontal vertical, I can pinpoint to a square millimeter space. So if I just remove one part, I'm basically doing what? I'm basically zooming out of my picture and rather zooming in on my picture. Okay. So when we add, so when we are adding more bits to the right, or basically when we are doing more splits of my geography and then trying to add more bits and basically adding more bits to the right part, we are adding more precision to our number, which means we are actually zooming in. क्योंकि उतना अंदर जा जाके we are checking कि who are the neighbors of this part. And when we are skipping the right half, because when you just consider this much of it, like one, we are basically zoomed out of the world and we are just seeing the right half of the world. Correct. So basically on Google Maps or on Google World, when you are constantly zooming out, and you see the entire world. Correct. इसका मतलब है कि it's like this sort of representation where it is nothing gets represented. Then let's say you made a one scroll in and you are now focusing on the right half of the world. So then it's like just having that one over here. If you are zooming in the top half, it would be 1 0, right? So this way you are actually zooming in and zooming out by cut shorting or extending the precision of this binary representation. So this is also a very good way for you to implement zoom in and zoom out. One of the algorithms that we studied during our computer graphics, I never knew it could find its way into a hyper local sort of use case. So something that I learned during my second year undergraduate course. So this is exactly how we implemented zooming in and zooming out on 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 a 2D object. We were given a picture and we wanted to implement the functionality of zooming in and zooming out efficiently, and we accidentally used this part. So it was algorithm part of our textbook. We implemented it, but when I was studying, when I was using it at that point, I realized, yeah, this is exactly what I studied in my second year computer graphics course. So yeah, somehow everything is linked. Matlab, from computer graphics to geolocation, like the core remain the same. Okay, so you can leverage this part wherein, like, even though you would have like good amount of digits here, it's not that digits are not here. It's just that you are not using it to for part of your computation. That's it. Okay, when you're just focusing on the first step, so you'll find out all the people who have this prefix like 100 110, you'll find everyone who is part of this block. As simple as that. Now let's say you want to zoom out and let's say you want to find out everyone who is part of this. You'll just you'll just remove 10 from here. So everyone who is of 10011, then you have basically effectively zoomed out to this part. Similarly, if you would want to zoom out to this part, you'd just then remove this much. You'd say 10. Every people who start with 10, I'm doing this. So if you are making that location slider, what's the radius that you are looking for people, like find me people who are in like 20 kilometer of the radius. You are effectively doing this. You are effectively just removing 10 out of, or basically one bit out of it and then matching it there. And once you're narrowing your scope, give me just people who are just within 1 kilometer of my radius. So you are just adding more and more bits to our representation, saying, I just want this should be the prefix that needs to be matched. So effectively, any data structure that could help you do a very efficient prefix matching is what you should be using here. We'll talk about which data structure to use to solve this problem. But yeah, this is the heuristic, this is the intuition behind building a geo hash sort of stuff. Okay. So this is, if you're talking about a representation in terms of bits, so a 32-bit precision will take you to a square millimeter of the world. मतलब इतना है, मतलब one integer में 32, 2 raised to 32 तक जाता है. And when you divide it by that, you get like at a square millimeter के precision पे you can spot that particular thing. So उतने तक you can represent. So the although it seems like every time you would have to do that, but obviously there is a mathematical algorithm that converts your lat long into geohash ka code directly. Like you don't have to do splits, but split is what our intuition is, which is much more important to understand because you can use it at computational, you can use it at computer graphics and a lot of other places. So zooming in and zooming out, if you're trying to implement it somehow, you can leverage this part. Okay. So the only con that we talked about was like 2 points that are actually closer in the real world might seem too far away. Because one is in the left part, other one is the right part. So that is a little bit of edge case. Okay. In actuality, the 32-bit integers, when you talk about it, is not human readable. It's definitely not human readable. How can you even remember 32-bit string of where this particular point is? Right, so that's where the actual geocode that you'll see in action has alphanumeric characters. The base is changed, so the base of your 32-bit integer is changed to 30 of your 32-bit integer. It's basically you use like you you take that integer and you convert it into a 32, you convert it into a base 32 number, like similar to how we do an integer to a hexadecimal conversion. So from a base 10, you convert it to a base 16 by using characters A to F as well. So 0 to 9 and A to, A to F, correct. Huh? 0 to 9 and A to F. Here we change it to base 32. Right, so instead of 16, similar to how we do it with 10 to 16, here we are doing like bits, as in 32 bit, from bit to base 2 to base 32. Okay, and we add more characters to it. Okay, and instead of splitting it in two every time, we split the region into 32 blocks and doing a similar exercise. So the blocks are represented like this. Okay, so these are the 32 blocks in which, so in the heuristics when we're discussing, we're always splitting it by two, adding number 0 and 1, 0 and 1, 0 and 1, depending on how the split happens in top or bottom or left or right. Instead, what actual geocode does is it splits the region into 32 blocks. Okay, and assigns each block a character. So let's say C is the top left of the block. Okay, P is the bottom right of the block. Okay, so we split the region every time into this 32k pieces, and depending on where my point is, we basically pick that character. So it uses 32 characters 0 to 9 and A to Z except A, O, I, and L. Except this, they use all the characters. So you'd see like this is the order of it. So C, F, G, U, V, Y, Z, 9, D, E, S, T, W, X, something. Okay, so now when we talk about this, so let's say we are focusing on the top left part of the world. Okay, when we're talking about that, all the points on that part would always start with a C. While when you're talking about the bottom right, let's say it's so basically Australia would be somewhere around like J-ish or something. Okay, so anything, if you're talking about Australia, New Zealand, all the geocodes of that point, every point can be represented by, and the geocode of every single space or every single people who are online would all of those code would start with a J. Okay, India wala would come somewhere around this M or T or something. Iske around kuch to aayega. Right, so instead of doing it on 2, because 2 was easy for me to explain, we extend it to a 32 part. So entire space split into 32 repeatedly. So even that C block, once we got, we then split that C into 32 blocks, like with this same structure and the same proportion, and usme se we basically drill down our point. So this way, by doing like 7, 8, 9 iterations, so depending on what kind of depth do we need, we can continuously keep on adding those many, splitting the region into 32 and then finding out that point where it lies, and then splitting again, splitting again till the point we are happy. Okay, this is the actual geocode ka implementation. So now so okay, the nearest point are the closest string. The kind of data structure we use to do this, like for prefix matching, try is a data structure that you can use if you're doing a very hard prefix matching. But you can also check for edit distance ka thing. So instead of checking for a very strong prefix match or a pure prefix match, you can also check for like similar prefix match, because in some cases, in some geography, there might be like the entire code. Like for example, if I talk about this, yahan pe nahi, yahan pe, haan. So if I talk about this point and this point, prefix may there would be just one character change, baki almost सारी चीजें same होगी. So instead of doing a very hard prefix match, we can check for if the edit distance between the prefix does not vary by more than 2 or 3 characters or more than 2 or 3 bits. Then also the points could be close to each other, right? If you can actually work it out with an example, it's very simple to do it. वो वहां से if you can work it out, you'd find out कि the prefix actually alters by just 1 bit, and not at the fag end but at the middle part of it. Once you do that, so इसलिए फिर instead of just checking for a very hard prefix match, we check for the prefix, longest prefix with minimum edit distance. So 0 wala are actually the nearest one, and maybe with the 1 edit distance or 2 edit distance or 3 edit distance and all, they are a little farther away. Okay. So for that, you can use BK trees. BK trees are meant to find edit. And by the way, this is exactly what Elasticsearch does to implement fuzzy searches. Like we were discussing about information retrieval, so usme how can you implement fuzzy searches efficiently? So it basically uses BK tree to store all the strings which are separated by which are separated by edit distances, and through that you can find out okay, by for edit distance of 1, what are the closest strings to me. So you can look out for BK tree for edit distance based, and if you're doing a pure prefix matching, you can every time use try to solve this problem. Okay. One very interesting fact is when in 2015 time, there was a company which was started in India called Zipper. And what they did was they tried to give they tried to give a human readable string to every location of India. So what did they do is they went from building to building. They started their operation mostly from Hyderabad because that's where I saw that. They like for example, if the name of the building is let's say Aditya Apartments, so they went to the building since they were the early adopters, so they get to pick any code that they would want. So they write AADI07. So AADI07 was the code. So if someone went to their website and typed in AADI07, it would actually on the Google map, it would point to that very building. So you don't have to specify where your building is, go left, second right, third cross, fifth lane, beside a temple, under a neem tree sort of stuff. You can just share this one code, which would be your address, which is very easily recollectible. It would, you can very easily remember that part. So they tried that. Now they've changed their business model, but this was something that you can still find in Hyderabad. If you roam around the city, you'll see boards having this code and zipper written against it. The zipper company is still functional, but they have changed their plans, it seems. They were not doing it with geohash, but their idea was very similar. Even right now on Google Maps, if you open a location, it gives you a 8 or 9 character long string which you can use to basically search on Google Maps for. It's very close to geohash, very close to geohash. So you can still find traces of this in around the world. Okay. Now, obviously, theory very those are all okay. How do we implement this? Okay. Why geohash is basically such a beautiful thing? Because it's very easy for us to implement a very obviously at a low scale when we are not having enough people or enough users on the system. You can even work out on geo queries on a normal SQL database by writing a query like this. If you are building Tinder, let's say you want to find out, let's say, so TDR1B is the geohash, the actual geohash of Bangalore. If you go to geohash website and you type this TDR1V, it would point to entire Bangalore. Okay, so TDR1V is Bangalore. So if I want to find all people from Bangalore should come to my Tinder. Okay, if I want to do that, what I'm effectively doing is everyone who is having this as my prefix is nothing but are people who are close to me. Okay, because I've actually expanded my space to like entire Bangalore I want. So it's as simple as select start from people where substring of geohash comma 5. Basically, first 5 characters of geohash of all the people should match TDR1V. As simple as that. Then look, this could be the simplest SQL query ka solution for this problem. And you can very easily find out people who are closer to you. Basically, all the people from Bangalore should come to my Tinder account. Okay. And obviously, our favorite database in the world, Redis, also has this implementation. Redis supports geo queries out of the box, and it uses integer representation to do it. It has the code that converts lat long into this. So go explore geo queries on Redis. It's very easy to do it. You'll be amazed how easily Redis has implemented some of the most complicated data structures and has solved so much of problem for us. So you can very easily just put in key, okay, this is my user, and basically you can give a key and a geolocation against it, and then you can find out who all are near your place. So you can define, you can search it by kilometer, You can actually specify people within 8 kilometers. So 8 space km from this location. It would give you everyone who is within that, particular range, uh, that particular distance from your given query. And this is exactly what Uber, Ola, Google Maps, everyone uses a very similar, they might not be using Redis, but a very similar thing. If you want to build your own Uber tomorrow, you can actually use this part to build it. So Uber, you can dump every time, every once a while. Achha, we have enough time today. Let's build a high level system for this. So if you would want to build a high level system for this now, it will be as simple as you'd have a cluster of Redis nodes. And what you'll do is you'd use geo queries of Redis. Geo queries of Redis you can assign a key and a geolocation for it. Next time when you give a key and a geolocation for it, if the key exists, this key ka geolocation will be updated to the one that you have given. Okay, this is how it functions. The kind of gets you can make out of the system is what you can do is you can say this is the point, this is the distance, let's say 8 space unit, which is kilometer, and then it gives you all the points that are within 8 kilometers of your given point of the given point in the query. So this means if you have hundreds of users, let's say we are building Tinder and you have hundreds of users, all of this would be sending out their response, sending out their geolocation periodically, let's say every 5 seconds to your API server. And this API server is just storing this thing in Redis. Okay. Now, if I want to find out who all are nearer to me from a given location, the user would actually fire a query for that. The query would come to this thing. It would go to Redis. In Redis, you can make a geo get. I actually forgot the query. It's like people who are closer to me. I actually forgot the query, the actual command of Redis, but you can very easily find it. Redis command mein hai uska. And through this, it will help you get all the people who are near to you through this. Now imagine this being done by Uber whenever the rider app is on, or the rider app, or sorry, either the driver app or the rider app is on. It is constantly streaming out the location to a central server, basically this particular Redis cluster. And once it gets all of this part, you'd want to find kahan pe mera driver. So it just you can just do this with this part. Let's say ki, okay, who are near me or where is my rider, you can make a pointed query to the rider, and but where exactly is he, what road is he traveling, and para part. You can use this very similar thing to build restaurants near me, like Swiggy, Zomato, finding cabs near me, finding bikes like Yulu, Bounce, all of those things near me. Like, so anytime you open app and you see ki, yes, stores, yeah, let's say McDonald's near me or shops near me, and it basically pinpoints you around that. If you want to implement it, if you don't want to implement geocode on your own, Redis already gives it to you out of the box. You can actually leverage this part and build it in few hours. Half an hour में सब हो जाता है आजकल तो. ठीक है, so there are tons and tons of applications of geolocations and all. So yeah, this is all about geo hash. Any questions around this? Yeah, georadius is the query. Thanks, Piyush, for dropping me. Yeah, georadius is the query through which you can find out.
Are you aware about any live production systems like Zomato which are actually using Redis to solve this problem?
One of my friends works in the team that runs this on Zomato.
Oh, okay.
उसीलिए मुझे पता. Actually, while I was building this course, I've talked to a lot of people from a lot of companies to just understand are they actually doing this. So yeah, one of my very good friend works in the team that does this sort of stuff on Redis. And they're actually using Redis. Restaurants ke location they put on Redis. People ke location they go there and they find shops near me through Redis.com. And then basically my friend works in the team that serves advertisements. So geolocation based advertisements are shown to the people now. So they get a candidate list of restaurants, and this is an input to his system. And what it does is he, depending on advertisements and all, he actually rearranges the results, ranking, rearranging on the basis of relevance, advertisements and all, and then they surface out the result. So this is exactly what they are doing. Yeah, this is how you can build your Swiggy, Zomato, Uber, Ola, whatever you like. सब बना सकते हो इससे. Bounce, Yulu, shops near me, McDonald's near me. You just have to tag that thing relevant to that relevant course and to that relevant tag, and you can fire a query for this. So geo radius is something that you can use. Geo add would be something that would be used to add something to your database, and then through which you are constantly updating the location through that. So it takes in lat and long as an input.
So when we divided our like the whole set into 32 bits, right? So it would also resolve our issue when we had similar
to some extent, but वो boundaries ना आजू बाजू
extent.
वाले में still आएगा.
हाँ ठीक है.
अंदर वाले में नहीं आएगा, but बाहर वाले में आएगा.
समझा.
You मतलब there are ways to do it. There is something called as S2 geometry. Go through that. So that I plan to cover it, but वो थोड़ा ज़्यादा advanced हो जाता था, इसलिए मैंने फिर वो cover नहीं किया. S2 geometry, go to S2 geometry. You'd find a very similar concept to this, and people from other companies, they actually Uber uses S2 geometry. Uber के blog पे लिखा है S2 geometry to solve this problem. But at the end है सब एक ही चीज, सब एक ही है.
क्वार्टरीज भी ऐसे कुछ होते हैं.
हाँ ठीक है. So this divide and now basically we talked about divide and conquer. Now one thing that I would really want you guys to do it, like this sort of divide and conquer strategy is also used to find anomalous points from a data set. Now that we talked about geocode, now you'd say geocode kaha, anomaly detection kaha. That's the beauty of computer science. I started from computer graphics to geolocation, and now coming to anomaly detection. Three totally dissimilar fields, right? But what binds them together is this one strategy of divide and conquer, the way we saw it. This one strategy, like splitting it into half, or some n number of blocks and doing it. I've written long time, about a year back, I wrote an article about isolation forest algorithm for anomaly detection. Read that. Going through this geolocation, you'd find so much of similarity into it. It will be very easy, breezy read for you guys. Go ahead and read that. It would give you how, it would tell you how to find out anomalous point. Basically, if you're discussing with about anomaly detection, you can always talk about isolation forest algorithm. It's a very good thing. I stumbled upon isolation forest algorithm in a Groffer's blog. So Groffer, that grocery delivery app, apna India wala, their technical blog mein, about 3-4 years back, they wrote an article on isolation forest algorithm. That's where I stumbled upon that term, and I just read the paper and wrote an article myself, pura detail mein, with implementation in Python. Go through that. It's a very, very interesting read. How can you detect isolation? How can you detect anomalous point out of your system? But the algorithm is very similar to geocode, very, very similar. ठीक है, मैं बहुत सारी चीजें पढ़ने को बोल देता हूँ, बट हाँ effectively I cannot cover a lot of part, but अगर आखिरी में टाइम बचता है, I would love to cover the isolation forest. This is one of my most favorite algorithm out there because it's so intuitive. You after reading it, you would say कि अरे ये मैंने क्यों नहीं सोचा, इतना simple है ये. बहुत मजेदार है algorithm, isolation forest. Do read it. ठीक है. अच्छा, ये थोड़ा बड़ा जाएगा. Let me cover the third problem first and then we'll go on a quick break. Third one will be very quick one. उसको पहले cover करते हैं. ठीक है. Now that we are talking about geolocation and all, you say you traveled by flight and you reached your destination. Let's say you were traveling from Delhi to Bangalore. You reached Bangalore. You took your phone out of your airplane mode, and what you saw was Uber's, and you opened the Uber app. Uber app पे पहली स्क्रीन दिखते है welcome to Kempegowda International Airport. कैसे पता चला? How did Uber identify that you are in Kempegowda, not in Bangalore, but in Kempegowda International Airport? This is very interesting of a problem. Like even from a perspective, like if a landmark is big enough, let's say the first time I went to Hyderabad, Sujana Forum Mall was there. I went there, and at that time it was very early days of like Uber, Ola and stuff, or Uber, Ola, Swiggy kind of thing. It was like 2013, 14, 15 wale phase mein. I went to that mall, and to my surprise, I opened the Uber app to basically go back to my hostel. Yeah, it should be in 2014, 2015 this time. So to go back to my hostel, I opened the Uber app. Uber was very new to that at that time. And what I actually found was it asked me, he will I be picking cab from gate A or gate B? I'm like, Are Bapre, matlab, it's not just saying ki bhai Sujana Forum Mall. It's even doing micro tagging on it and saying ki gate A or gate B. I was like blown by it. कि इसको ये कैसे पता चला कि कहाँ हूँ मैं मतलब within that micro tagging it actually did that. It identified that I was at Sujana Mall, and within that it then suggested कि I could go for gate B, जहाँ से इतना time लगेगा, यहाँ से गया तो इतना time लगेगा. And I was blown by that fact. How does it, and then obviously when we travel and we go to airport and all, it says welcome to airport, welcome to this, welcome to that. Every app today, but now today it's a norm. But when I first saw it, it was like, अरे बाप रे, इसको यहाँ तक पता है. And this is the beauty of it. And now another extension of this problem is when Swiggy, Zomato, or Amazon delivery people come to it. If it's a gated community, let's say there are 8 or 5 different wings. It actually, if you open Google navigation, it would actually tell you, let's say you put in your address as E204, as in the E wing, it would actually navigate you to the E wing. And once you reach the front of the E wing, it would say, ki, Arey, your home is here. Instead of saying, ki, Arey, pura wo gated community ka dal diya, to wahan pe khatam ho gaya. Nahin. So this micro wala part where it identifies that you are within this space and then it helps you navigate. This is made possible only when you identify if a point is within a polygon, right? And this is what algorithm that I would like to talk about. Okay, because now this would open up a plethora of applications ki kya kya nahi kar sakte. Right? So this is the core problem. Given a point and a polygon, find if the point lies in the polygon or not. Very simple, right? So airport, obviously there is a fixed boundary. If the point lies in that polygon, matlab wo point uske andar, and then you can initiate your micro tagging wala flow. And basically once you have identified that you are at basically this, other than that P is you and this boundary is the airport's boundary. Once it identifies that P is within that polygon, it would say, welcome to Campecola International Airport. As simple as that. Build this to make location based reminders. You can say, this is my home. You can mark your boundary in the app and say, whenever I come to this point, automatically put my phone on silent. Let's say once you go to office, automatically put my phone on silent. You move out of office, you can. आजकल तो norm है. In 2012 I built this application and I was so happy that I built this location based reminders. I used to very shitty code, but that was my first ever Android app that I built, location based reminders. So when you go to a particular place, it used to send me a reminder, this ye karna hai, wo karna hai wala part. So let's say we are at a shopping mall, or for a grocery shopping stuff, you are at the supermarket and it should remind you, ye 10 cheez leke aani hai. Right, that flow. So this is, if you're trying to build a system around this and want to know the algorithm behind it, so ye hota hai. So you can very well use Redis, but obviously if you're discussing with someone, would say Redis ne kaise implement kiya, or when you're talking you'll use Google Map API, but then the point comes out how would Google have implemented it, right? We are talking about that, but how, if given this problem, how algorithmically is this solved? It's a very simple math wala, but you'd say simple math, ekdam simple. So the type of polygon we're talking about are convex polygon. So convex polygon may you pick any 2 points within the polygon and you draw a line. The line would also remain within the polygon. So this is a convex polygon, and the concave polygon is something like this. Okay, so if I pick this 2 points, the line lies within the polygon. But if I pick these 2 points, the line crosses the polygon and is actually partially out of the polygon. Okay, so this polygon is a concave polygon, while this one is a convex polygon. So what we're talking about here is a convex polygon if a point lies within a convex polygon. Okay, And the algorithm that we'll talk about is called as ray casting algorithm. It's exactly what its name says. Like ray ko cast karo and see ki ray kahan jati hai. As simple as that. So the idea for this is you have a point P, right? So point P lies in the polygon or not. So you'll cast a ray from point P going horizontally towards the right side of it. Okay. If this point intersects the polygon odd number of times, तो point अंदर है, right? If the point, if the this ray intersects the polygon on even number of times, then the point is outside the polygon. Okay. And obviously the edge case, if it crosses the vertex or it's parallel to the edge, then it's a वो obviously edge case है, वो ये अलग से implement कर देंगे. ठीक है. See, this will make it very clear. So point P is, so if I started a ray from point P moving towards the right, it intersected the polygon in this one point, right? Since it is odd, the point P lies within the polygon. If point P is here and I've created a ray, it intersected the polygon at 2 points. So point P is outside it. Try, no matter how many times you would want to try it, this would always hold true. Okay, so odd and even wala rule applies here. Okay, so this is what, and basically this is not something like not used. This is what it's used to find out if a point lies within a polygon efficiently. So काफी अच्छा ये है. So यहाँ पे one very interesting thing that we would also discover is how do we represent a polygon, right? मतलब whenever we are talking about geometrical algorithm, the सबसे पहला challenge comes out कि given this problem statement, how do I even represent a polygon? कि कैसा कौन सा data structure and क्या करूँ, right? So a typical way to represent a polygon is using an array of points, and these would be like ordered edges. So for example, I would have not edges, I'm not storing edges, but I'm storing points which are ordered by edges. For example, so if my polygon is A, B, D, C. So janbuj ke I have just flipped the other two so that I make it very clear. So A, B, D, and C. Okay, if this is my polygon, a polygon for me would be represented as A, B, D, C, which means when I take two, basically when I take pair of points which are adjacent, so AB, BC, DC, and CA, right? तो मेरे को edges दिख के आएंगे. So the AB, BD, DC, and CA. AB, BD, DC, and CA. So these are my ordered edges. So this is how I can efficiently represent a polygon. In most geometrical algorithm, wherever you have a need to represent a polygon, this is what you can use. सारे algorithm होते हैं. So similar to how graph पे there is adjacency list and adjacency matrix representation, ये polygon का edge, this sort of representation is very common for polygonal wala use case. So as an ordered set of points which are ordered by edges that are there. Okay, and each point is nothing but a coordinate x comma y. So so x coordinate and the y coordinate of that point. So b ka x b, y b, d ka x d, y d, a ka x a, y a, whatever it is, वो उस तरह से it represents. So every point is x comma y, and polygon is a array of points which are ordered. This is very important, ordered by something, because then only, otherwise edges अलग से store करनी पड़ेगी. But if it is ordered, representation is very easy. Okay, so the idea is exactly what we discussed. We start from P and we project our ray towards the right side. It goes till infinity. Okay, ray starts at P and goes to infinity, goes to the right towards infinity. And what do we do is we count the intersection that we have, and we basically count it. If it is odd, to kuch, even to kuch. Okay, odd to inside, even to outside. So for each edge E, we find if, so now our problem statement is simple. Okay, since we just have to count the number of intersections, we have access to all the edges. Representation is solving that. Now what we typically want to do it is we just want to find kitni baar wo intersect hua. When we want to find out how many times did it intersect, our problem statement now boils down to, for each edge E, find if the ray intersects. If the ray intersects, then you do plus plus. Your count intersection becomes plus plus, otherwise minus minus. Okay. So what do we do is each edge is now represented because edge is what? 2 points A comma B. Okay. So what will we do is we will arrange these points such that, matlab, basically swapping wala logic. Okay. We are just arranging it such that x1 comma y1 comma x2 comma y2 for y1 less than y2. So I'll always have my 2 points of my edge AB, because like my edge AB ho ya BA ho, it's exactly the same, right? But for me, I'll just flip the point for my computation benefit such that x1 y1 comma x2 y2 such that y1 is less than y2. So the first coordinate will always be y axis pe niche and second coordinate will be y axis pe upar. So it will always be A and B. A, matlab, sorry, basically when I talk about point P1 and P2, let's say. So this will be P1, P2, P1, P2. So when I'm talking about edge AB, I would have A as my P1, B as my P2. And when I'm talking about edge CD, I would have D as my P1, C as my P2, because Y1 is less than Y2. Okay. So if we arrange this, our problem set actually becomes very simple. We will always know that Y1 and Y2 are arranged like this. So Y1, Y2, or rather P1, P2, sorry, Y1, Y2, Y1 is less than Y2, so P1 and P2. So this is my P1, this is my P2. Now what are we doing here is, if the ray intersects or not. Okay. Since we are starting from P and moving towards right towards infinity, moving to the right towards infinity, if my P is above Y2, then my ray would never intersect. Correct? B के ऊपर कहीं से भी जाए, my ray would never ever intersect my edge. Correct? Then A से नीचे. So anything, if my y coordinate of P is less than my y coordinate of A, then it would never intersect. So this went from here, this went from here. Correct? Again, if my point P is on the right side, if my point P is on the right side of my rightmost point. Okay. So ये नहीं है, but if it lies within that, within this thing, within y1 and y2, and if P is on the right side of my rightmost point, then my ray would never intersect. Correct? Now, if my point, so this three cases pe ray will never intersect. If above B, below A, or right side of the rightmost point. Okay? So these pe, if you know that this part, then edge would never intersect. The fourth case, where P is on the left side of the leftmost point. So P is over here. This is where it would definitely intersect. It would definitely intersect the edge. Okay. At this point, it would definitely intersect the edge. So यहाँ पे count plus plus. So this is what we will do. So we'll do the sequential checks. We'll first check if P is above B, then no. If P is above B, then no. If P is below A, then no. If P is to the right of max of A comma B, then no. So right of rightmost point, then definitely no. But if P is on the left of the leftmost point, then definitely yes. Whatever, because now what we have done is above B, matlab this region went off. Below A, matlab this region went off. On the right, matlab this region went off. Okay. And what we are checking for is this. This is left of this, so it will definitely intersect. Okay. So ऊपर का काटा, नीचे का काटा, right का काटा, left वाला is definite yes, but only when P is on the left of the leftmost point. Okay. Now comes an interesting case where P is not to the left of the leftmost point and not to the right of the rightmost point, but basically P is lying either here or here. So यहाँ पे क्या होगा? Because you know, if it is here, then it is intersecting. If it is here, then it is not intersecting. Okay, so this is where we have to apply the logic. कि क्या करना in this case? Will my ray intersect or not? Okay, this is that one case that we have to explicitly handle to find out, because if it was on the left of the leftmost point, then it will definitely have. But if it is not on the left of the leftmost point, मतलब इसके और इसके A और B के बीच में है on the x-axis, then it can intersect or it cannot intersect depending on where P is. Okay. Now this is where the challenge lies. How do we identify this? So bounding box checks are done. Sanity checks जहाँ पे definite surety है कि it does not intersect or it intersects. This is where things become interesting, where we want to find out if it would intersect or not. Okay. So here we cannot apply the bounding box checks because depending on where the point P is, it will or won't intersect the edge. Okay. So how do we address this? Any suggestions? How can we address this? Sure. I'll cover. Simple. सब पढ़ा है अपन ने. Slope. Slope is what we can use to see if we can use slope to identify where my P is. Right? If my P is above or below, what is slope? Slope M is equal to y2 minus y1 upon x2 minus x1. Correct? The value of M changes from 0 to infinity. Okay, so this is how my slope would change. Like, so if it is parallel to x-axis, my slope is 0. If it is parallel to y-axis, my slope is infinity. Okay. So if my point, so what I would do is, let's say my point, so my point could be like P dash or P double dash. So what I can do is I can compute the slope. Let's say I'm talking about P double dash is where my P is. So I'll compute slope of AP double dash and AB. Okay, if my slope of AP double dash and AB पे relation is slope of AP double dash is less than slope of AB, then my line would not intersect. Okay, but if the slope of AB is less than AP double dash, or rather slope of AP dash is more than slope of AB, then my ray would intersect. Correct. So you can just simply leverage the part, you can simply leverage the fact that you can simply compare the slope of your actual edge and a hypothetical edge between your vertex, like your bottom vertex and the point P. So AP and so AP be it wherever it want to be, but since we have rearranged the point, this is possible. So check करना आसान हो जाता है. Okay, so we compare slope of AB and AP. So if slope of AP is greater than slope of AB, okay, if slope of AP is greater than slope of AB, then yes. Example AP dash, right? Slope of AP is greater than slope of AB. Okay, and if it is slope of AP is less than slope of AB, then no. Right? So एक जगह intersect होगा, एक जगह intersect नहीं होगा. So just by comparing the slopes, we can identify if my edge is, if my ray would intersect or not. So bus normal mathematical calculations can very easily help you find out if point P lies within the polygon or not. Any questions? Again, या तो समझा या तो कुछ नहीं समझा, but ठीक है. Even if you guys didn't understand, go through it once again. Right? All of these algorithms, these seems very mathematical. Definitely, it is not as tricky as other mathematics thing that we have discussed or there are in the market. But there's something that we need to have as a good problem solver. See, how do we even approach the problem? It's just like basically taking down a problem, making splits here and there, understanding कि, okay, this is definitely false. Like this is what we do with competitive programming, right? Edge cases. इससे ज़्यादा है तो definitely no. इससे कम है तो ये नहीं करना है. And then you basically boil down your problem statement into something that is challenging, and then you address that part. We took the same approach and found out how do we identify if a point lies within a polygon. We boiled it down and brought it down to a point where we say ki if my point is, we just want to find out if a point intersects any edge, we'll do it for all the edges. We'll do a count plus plus wherever it intersects. As simple as that. So once we do that, we get even and odd. Depending on that, we'll say if it is lying within the polygon or not. Okay, so we have basically split the problem statement into smaller part, Then we solve it and then aggregating it and eventually saying if my point is lying within the polygon or not. This is a classic raycasting algorithm that helps us identify this. And this is exactly how we can find out if uh, basically Google Maps find out if you have reached your home, and a lot of location based app where you can have a custom themes for your phone depending on where you are happens, like put phone on silent when at a certain location, like IFTTT does this. When you reach a certain point, give me a gift. When you do this, do something like that, like for example Pokemon Go sort of stuff, right? You can build a lot of fancy stuff around it, like when I reach a certain space, alarm me basically whenever a Pokemon is near me, or when I travel to a Pokemon. So many places you can find it application. So anywhere you'd want to find out if you are part of a room or a location or what I can say, or an attraction place or some sort of bounded box, this is what you can use. Okay, so this is the third part that I wanted to go, जो मैंने थोड़ा पहले कर दिया. Okay, समय की मर्यादा को देखते हैं. And we'll go on a quick break if there is no question, and then we'll talk about something that is very prevalent in Neuralink, Datadog application monitoring tools. यहाँ पे थोड़ा और ज़्यादा maths है. But obviously, when you are building some disruptive product, math तो आएगा. उससे तो you cannot shy away. Okay, but then you would have to understand where you can leverage those parts. So, any questions? Or we go on a break. चलो, silence पे मतलब break लेते. चलो, let's meet at 5:15, and then we'll talk about the final algorithm that basically helps us address the problem. How do we efficiently identify nth percentile from a stream of numbers? So just imagine where you can use it, like Neuralink, Datadog, AWS, CloudWatch Pay, CPU metrics are there. Your response time ka data is there, and you find out what is the 99.99th percentile of your response time. What's your median response time? Like very efficiently if you want to do this. Okay, this is the final thing that we'll talk about. Is nth percentile from a stream of numbers efficiently. Okay, chalo. See you guys. Let's thoda extra. Let's do it at 5:20. Okay, 5:20 we will start this. Chalo. Thanks, guys. let's jump to the final problem of this thing. What we'll do is we'll find out nth percentile from a stream of numbers. So this is a very oversimplification the uh, of the actual problem that it could solve. Like, just see the breadth of this algorithm. Like, you can find out so many places. Response time ka nth percentile you'd want to find out. You'd want to find out like clicks that happened on your system at what time, and like for example, this thing even in edtech, uh, there was this very famous game that popped out that actually compared, or malab, it was very early days like 2008 2009s of Facebook, where there was this very nice addictive game in which it used to check ki how fast can you click your mouse, and then it used to say ki what was your fastest click, what was your slowest, or basically what was the quickest interval, or what was the smallest interval between two clicks of you that you made in last 1 minute, and what was the biggest interval. So this way you can basically, you can do your best around this. So with some very random hypothetical game, but yeah, people used to make like hundreds of clicks in more than 100 of clicks per minute, and then करके मारते थे, and then it used to give all of this fancy metrics out. So although it did not have to deal with this big of a data, no server-side computation on the client side would be good enough. But still, it was a fun if this could be extended to a scale, तो कैसे करेंगे? ठीक है. So what happens is, let's say we talk about a case where you are measuring your API server's performance or your application's performance by measuring the response time of each of your API. Now, if you're building that, you would have a stream of integers or a stream of floats or stream of numbers that denotes response time for your APIs. Now, from that, you'd want to find out what's the median 90 percentile, 99 percentile, 99.9 percentile of it. Okay. When, or obviously the number of APIs coming to your system could be millions per minute, right? So you cannot like store all of them, sort it and do it like, matlab, at scale, this would break if you just do it like naive way. And even if you do it on using batch processing, if you try to do it, it might take a lot of time for you to even come up with that. But Neuralink, Datadog, all of these APM tools exist, and they give you this sort of counts in like near real time, like with just like 5 minutes of delay on AWS, it gives you 5 minutes of delay. Neuralink is also, I guess, 5 minutes of it. But you can obviously tune it and say, okay, I want real-time data, and it actually gives you real-time what's the percentile that's coming there. So how does it identify? And obviously, this is not just one stream of data. So you can give any time range at the top. You can select any time filter, maybe last 10 days, 30 days, 7 days, minutes, may hours, may weeks, may or lifetime. It would give you it would give you those numbers. Okay, so how does it do it? So basically, to put it simple terms, accurate counting is costly. This is what we established like after talking about yesterday's impression counting as well. And even here, when we talk about accurate counting, what would happen is, let's say you get million requests per minute, and if a time filter is of, let's say, 30 days, so kitna data ho? So million requests per minute, and there are so 60 minutes in an hour, 24 hours into 30 days. Those much of data उसपे analyze करके you want to find out percentile. To find out percentile, you would have to sort it and then find out where it lies. It's a messy problem, right? बहुत time लगेगा, बहुत computation power लगेगा, so not a good way to do it. So that's where what we do is we give up on accuracy, and basically that's where a lot of a new class of algorithm has come up with, say, which are basically online algorithms. So these online algorithms are basically, they give you near accurate answer, and the accuracy is at like 2 to 5% error rate from the actual accurate answer. So matlab 2 to 5% ka error rate is, so, and obviously this is configurable. So depending on how much of memory you would want to use, if you use more memory, then it would give you more accurate answer. If you have constraints on memory, it would give you less accurate answer. So depending on what works for your system, you can tune the algorithm at your needs. Okay, but what it definitely gives you is, it gives you like immediate answer. Like, it does not wait. It does not do a lot of heavy computation. but it gives you very accurate answer, or sorry, it gives you answer very quickly. So like for example, if you make a call to any of this sort of data structure or any sort of algorithm like this, it won't do heavy computations. Like Mara, you fired a query and you'd immediately get a response, but this would be an approximate response and not an accurate one. Okay. Product like Neuralink, Datadog, CloudWatch have to use these algorithms because they cannot compute quantiles using brute force because scale is massive. And another example would be like Google Analytics ka click count that comes in, like what's the percentile of click count that happened on a day or whatever it is, like बहुत सारा analytics, basically analytics on top of numbers, percentile on top of numbers. यहाँ पे another challenge that comes in, like billions of measurements per day, plus with Neuralink, Datadog and all, another challenge that comes up is grouping, dissecting and finding out patterns and whatnot. So वो तो अलग ही problem है, but here at least finding 99.99 percentile very quickly should be, plus split across your cohorts, like geo group cohorts, user segments. You create custom user segments, you'd want to compute around that. So all of these things, like kaise karoge? Like there are much breadth of the system that we're dealing with here. Anywhere you see percentile, think about this algorithm. Okay, some lag on my end due to camera, but it's working. So accuracy requirement. Now comes the point where we start building our intuition. Okay. So this is something that we could have also leveraged yesterday during impressions counting. Okay. Hear me out. What do we need is we need a higher accuracy when we have fewer points. Okay. Let's say you are very new to LinkedIn, and what do you have is every like matters. Like every like you get notification, you get the dopamine kick, and every like matters. So when you see that I got 10 likes, you are very pumped about it. This cannot be approximate. You click on it and you go and you find the 10 people that have liked your post. Okay, this is where your accuracy matters. Now where accuracy doesn't matter is when you have millions of followers. When you have millions of followers, and let's say you got like 50,000 likes, will you go through those 50,000 and see exactly 50,000 hone chahiye? Right? That is not what you expect out of this thing. So when you grow, when your volume grows, it is okay for you to be less accurate. So when you have fewer points, you need very high accuracy, right? It should be near accurate. But when you have far too many points, your accuracy might stumble. Okay. So for example, till now we saw only 10 points. Measuring nth percentile should be accurate. But when computing, now this is another use case. So when we typically say when we have too many points, then you do this. But here we are talking about percentile. But when we have too few points, we need higher accuracy. And when we are computing higher percentile, not too many points, right? When you're computing higher percentile, we also need very higher accuracy. Why? Because 99.99 percentile, matlab that out of, let's say if you're just talking about like, let's say 10,000 requests in all. So 99.99 percentile, matlab that one request that is the outlier that takes the maximum amount of time. Okay, so this cannot be approximate. Because, and basically this has to be more accurate. Why? Because even a point here or there could actually tune or could actually give a very wrong indication. For example, let's say you have 10,000 points, out of which first 9,999 points have value from 0 to 1, right? Sorry, have value from, let's say, 1 to 10. Okay. But that one point, uska response time went till 2,000. Now, if you take this thing if you don't have this thing accurate, and let's say the maximum value is 2,000, the second max value is 11, or let's say 10. Okay, so if you have skipped somehow, made this thing less accurate, you would see a 99.99 percentile to be 10, which is not true, which is actually, it has to be that massive value of 2,000. Correct. So when you're talking about massive percentiles, you'd want this to be very accurate, because even a small deviation, even a small here or there thing could make a very massive difference to the value, because there are too few points in that range that is to be picked from. Okay, this is why you need higher accuracy when you have fewer points, and you need higher accuracy when the percentile you're computing is massive. Okay, this is very important to understand. Like this would form the crux of our algorithm. Like this need. Okay, so and obviously when we're talking about a median of this sort of thing, like when we're talking about this 10,000 points, 1 to 10 पे सब vary के, and then one is like 2,000 पे, यहाँ पे for this use case just imagine we are computing median of it, ज़्यादा फर्क नहीं पड़ेगा, right? Because there all the maximum of the values are there stuck in this range of like 1 to 10, सिर्फ एक बाहर है. So what would happen here is that one value, if you're talking about 50th percentile, the median of it would have very low deviation amongst the value. So here, either the hua, then it still would not matter because it's all clubbed together when there is a lot of points. Okay, this is very important to understand. Like this forms the crux of our algorithm on how our algorithm would treat this thing. So what we are actually talking about is an algorithm called as, or a data structure cum algorithm called as T-digest. So T-digest is the name of it. You can read research paper about it. There are quite a few of resources, not good ones though. But uska research paper is excellent. I've gone through that. मतलब मजा आ गया था पढ़ के वो. The idea of T-digest is basically doing k-means clustering in one dimension with varying cluster size. Yes, this sounds like too much of fancy words, but it is very simple. Okay, just see this. एक मस्त diagram बता दो ना, फिर I'll come back to this. See, this diagram would make it clear. So what we are actually doing is, when you are computing, so on this axis, these are all the points which are plotted. Okay, so the median wale points would come around here, right? This is where the extreme percentiles are computed. This is where like lower percentiles are computed. Like, so we need smaller cluster size to compute this thing. So we can approximate quite a bit over here and too few over here, right? So यहाँ पे maybe 1 point का मतलब a point, मतलब here the cluster size should be small, which means that 1 or 2 points in one cluster, 1 or 2 points in one cluster, right? But here there could be hundreds of thousands of points in these clusters which lie over here. Okay, वही logic है उसका. So now what do we do is let's say we have a sample data point. So the idea is we sample the data points. मतलब obviously when we would want to compute this part, let's say when we would want to compute what's the response time of it, if you are storing all the data points, then the space store nahi hua. And if you're doing the computation around all the points, then you are not actually, then you can never save on time. You can only save on space and time when you sample the data. So from the actual stream of data that you get, you have to sample the information and basically form clusters about it. So the idea is, let's say you are given 10,000 points. Out of those 10,000 points, you just pick 100 points. But these 100 points should represent the distribution that these 10,000 points actually did, right? And this distribution should be very, very, very similar when we plot it for this 10,000 point or for this 100 point, because then that's when we can get a very nice approximation of the actual value. Okay, so coming back to the cluster size, now what do we do is when we are talking, so our cluster size should be, so on the y-axis we have cluster size. So our cluster size should be large. Our cluster size should be large when we are talking about, so basically this is your cluster size, and your cluster size should be small when the percentile that we are talking about, when the percentile we are talking about is low or high, but your cluster size can be high when we are talking about 50th percentile or something. So your curve should go like this. So your cluster size should vary like this. So what's a cluster? So what are we actually clustering? So the sample data that we have, the kind of samples that we are putting in. So let's say we are sampling the data and we create a batch of all the metrics that we are getting. Okay, and we create this batch, and instead of storing all of them, we just store one that represents that cluster. Let's say I got 50 points, each point with the value of 10. Okay, up till now I got 50 points. Every value is exactly the same of 10. So would it matter if I store all 50 values, or I can just store 10 and say I got 50 values that represent 10? Okay, so instead of me wasting 50 rows of my table to store 50 different values, I'll just store one row which says 50 value. Oh, sorry, where I say that I got 50 points, and the value that is there is 10. So all the all the points have the same value of 10. So 50 and 10, rather than storing 50 rows each having value 10. Okay. So the idea here is very interesting. So when we are building a system like New Relic, we would get a lot of metrics that will be ingested into the system. Now, when this metrics would be ingested into the system, we buffer it for some time, right? The actual number. Okay, these are the actual metrics that are flushed into the system. We buffer it in a small chunk, in a small batch, let's say 1,000 ka batch, and we sort it. Okay. Once we sort it, then we cluster it, and then we store the centroid of it. And my camera is stuck in. Let me just turn off the camera. I'll just move to the basic camera. It's better if we थोड़ा सा quality गिरेगा, but ठीक है. It's better. पता नहीं क्या हुआ. A little low in quality, but ठीक. So the idea is when we get the actual stream of numbers, we have to sample the data. That, and this sampling way, what we do is we put all of this data in this buffer and we sort it. And then we sort it, we create clusters out of it, and basically we merge it with the global set of clusters. So the clusters ka centroid would be the representation of one value of that cluster. Okay, and then we say, okay, how many numbers were there in the cluster? Like something that we something that I talked about, like let's say I got 10, 10, 10, 10, and so on. We got it 50 times. So instead of making 50 entries in the database, what I'm doing is I'm saying I got 50 entries, each value 10, or rather each ke jagah pe I'm just defining one value which is 10. Okay. Now let's say this 10 is nothing but the centroid. Now here all the values were same, it became simpler. But then instead, let's say I had values which range from 1 to 10, 10 to 1, something, something, something. And I got 50 entries like this. And when I got this sort of values, let's say I computed a mean value of it, and or rather median value of it. And let's say my median came out to be, I'd say 50 entries, and my median came out to be 8. So if the median is 8, I would store 50 entries with 8 as the median. Okay, so what I'm doing is I'm actually saving out on a lot of space, right? Because if I store all the data points as is, then the फिर क्या optimization होगा, right? Then the approximation है नहीं, it's actual computation. When we do actual, it becomes very slow at billions of data points per hour के ingestion rate, right? So this is where we have to sample the data, but the sampling is not just like picking any random point and just missing out on other. The sampling here is being done smartly, which is by identifying how this data would be stored and represented and would match the distribution of my source data. Okay. So the idea example okay. So let's say these are the points. So this top row, these are the actual data that is coming into my system. These are, let's say, the response time of my APIs in milliseconds. Okay, these are the APIs of my response time in milliseconds that is streamed to my New Relic ka server. Okay. Now, once I get this data, let's say this is my one batch. Let's say I've hard coded that my batch is full when I have 1,000 data points. Okay. Once I have 1,000 data points, what I would first do is I would sort this number. I would sort this number, so I would get 1, 1, 2, 2, 3, 4, 6, 8, 8, 8, 10, 10. This is like 1, 2, 3, 2. So the numbers
The actual numbers which I got was 1, 2, 3, 2, 1, 2, 4, 6, 8, 10, 12, 10, 18, 10, something like this. Okay. What I would do is I would first sort it and then I would create clusters out of it. So I have sorted this number and I got 1, 1, 2, 2, 3, 4, 6, 8, 8, 8, 10, 10, and so on and so forth. And now what I would want is I would be creating clusters out of this, because what I would want to do is I would want to represent, I would not want to store all of these numbers, but I would want to store one number from each cluster. Okay, so how I'm defining cluster size? So the way I'm creating clusters is, let's say I say that my cluster would break when the lowest value of my cluster and my highest value of my cluster is having a difference of, let's say, 2. Okay, as soon as the difference between the lowest value and the highest value of my cluster goes beyond 2, I'll break the cluster. So 1, 1, 2, 2, 3, this becomes my one cluster. Okay, 4, 6. So here this would have become my second cluster and this would have become my third cluster. Okay, so this was like a very fixed rule which I can apply, where I can say that the difference between the lowest value and the highest value of my cluster can at max be 2. When I'm defining this thing, and now if I take a median of this value, it would be a very accurate representation of this cluster. So let's say I talk about this. I have 1, 1, 2, 2, 3. I can say that the median value of this is 2, and there are 1, 2, 3, 4, 5. 5 entries in it. Okay, so the representation of my cluster would be 2, 5. So 2 is the median value, 5 is the total number of points. But remember how we would want to change the cluster size, because for lower percentile or for each extreme, like be too small or too small of a value or too large of a value, because this is where your outlier would be and would define the distribution of your data. So you would want to have smaller cluster size for smaller values and for larger values, but you can have a larger cluster size for the common values, right? So your cluster size would grow like this and then would fall like this. So which means that instead of having that fixed difference, we say that छोटे values के लिए let's have difference of 2, बड़े values के लिए let's have difference for 6. So my first cluster came out to be 1, 1, 2, 2, 3, max value, max difference of 2. So representation is 2, 5. And now I have difference of 6. So 4, 4, 6, 8, 8, 8, 10, 10 became my second cluster. Now iska representation is 8, 1, 2, 3, 4, 5, 6, 7. 8, 7 is my representation of this cluster. Okay. And this is what, and now the difference, like smaller and larger value, this is not fixed. Here we're talking about 2 and 6, but this is typically given by a mathematical formula because it has to be agnostic of what input is coming in and has to be normalized. This was done as part of the research paper where there's this formula which they have used, but the intuition is exactly this. Okay, so smaller cluster size, because when this is a smaller cluster size, you'll get a very accurate representation of it. Okay, let's say there was this massive value. Hypothetically, let's say there was this massive value of 1000 here. Okay, but now we say that the cluster size should be small. Basically, smaller value and larger value ka difference can be at max 2 for the larger values. So यहाँ पे ये cluster इसका एक ही cluster बनेगा 1000. So this 1000 would be stored as 1000, 1. Right. So we are preserving the information that creates that basically brings the change in my data distribution. So we are doing a heavy approximation of the common data. We are doing very less approximation of the data which are outliers. So very small values, very large values pay. We are trying to preserve as much distribution as we can. And in the middle one is where we are doing a lot of approximation. This is actually very evident from this. So smaller cluster size, larger cluster size. Okay, the common values that are there, which are like 0.5, basically 0.5 is median, right? This is median of my system. So if this is the median of my system, this would have the largest cluster size and यहाँ पे smaller cluster size. So more accurately representing the data. Okay. Yes, Vishal?
Yeah, so basically our application is also using Datadog, right?
Hmm.
So our infra team, and basically our application is a spiky one. Okay,
Hmm.
so it spikes for few minutes, 1 or 2 minutes, and then for 10 minutes it's not there. The
Hmm.
load is not.
Hmm.
And due to this only, due to the spike, it is going to outliers. And while we have the system utilization of CPU and memory over the stretch of longer days,
Hmm.
the infra guys see that the system utilization is quite low because
Hmm.
of the graph
Hmm.
flattens out,
Hmm.
and because of which they keep on complaining that you need to cut short on your resource utilization. But actually, we are, yeah. So just wanted to make a point. So this
होता है
is
yeah
one of the negative point. Yeah,
yeah
because
वो
of this
होता है
out.
अभी वो भी क्या
Yeah,
करे ना वो हर एक डेटा पॉइंट स्टोर करेंगे तो उनका बिल बहुत बढ़ जाएगा
So outliers is good. In case your system is constantly utilized,
yes
then this would be quite helpful. But
yes
if you are having a spiky sort of a behavior, then
Hmm.
this will
Hmm.
not
yeah
be.
so this is where matlab since obviously a very fair point made by Vishal because since Datadog or Neuralink or any APM solution is not storing all the data points that you stream to it, it is basically storing the centroids of this cluster only. It becomes a problem somehow, right? So yeah, obviously the best way for them to do that would have been like to store every data point and do the computation on the fly on actual set of data, but that is very costly. So obviously they can't do that. Okay. Sure. The next part. So now this is where this comes in, right? So smaller value, for smaller values, for larger values, we'll have smaller clusters, and this for denser. And basically, you'd have like big clusters for the common values, and this is done for every batch, right? Not for global data. Once a batch of 1000 comes in, this is what it is represented by. Okay, so each of the values is getting represented by that one part. So let's say this cluster had like 5 or 6 values, उसमें से this centroid got registered. यहाँ पे this centroid got registered. So it is only taking up the space of this one centroid. So even though you had thousands of points, what eventually gets stored in the system is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 points only. So out of 1000 points that were actually part of the batch, it only stored 13 points. Okay, so saving of space. Okay, and now if space is reduced, तो time भी कम लगेगा because computation कम. जैसे कल देखा अपन ने with impressions, right? Lower amount of data, quicker, मतलब lower space required, तो जल्दी कम हो गया, right? And we compute the percentiles on the centroid of these clusters, and these centroids are stored as like any other, and other points are totally discarded. So once I have stored these centroids, बाकी के points we don't need that because the centroid is the representation of this node. ठीक है, तो बाकी सारे points are discarded. Now, now what I definitely have missed on is the part that although we are just storing this centroid, but the in truer sense what actually happens is मतलब आगे cover होगा वो anyways कि there are like finite set of memory for every data points का set that you have. So every distribution, every representation of yours, let's say you reserve, let's say 1000 points, जिस पे you try to represent your data. ठीक है, and this would represent मतलब how to put it, like with आगे आते हैं उस पे फिर cover करते हैं. This is nothing much यहाँ पे. ठीक है, this would help you cover that part. So यहाँ पे what happens is in this part you have 1 point for every 10 points is stored here, and यहाँ पे you have like massive big clusters. So again वो same part वहाँ पे कि you would have like far fewer points being registered for those big clusters. But now typically if I give you the number, this is some thing which I found on a particular blog. So 8 MB of measurements just took 5 KB of storage with a percentile error of 0.002, which is insanely small error, and 8 MB worth of measurements just required 5 kilobytes of storage. तो मतलब देख सकते हो कि just by giving up on like just 0.002% का error rate, you are getting such a big gain in your storage, which means faster computation. ठीक है. Now what would happen is हाँ ठीक है, इस पे कर सकते हैं. हाँ. Now that we know अच्छा ठीक है, did everyone understand the core of our algorithm? This is what the t-digest algorithm is all about. ठीक है, instead of representing all the data points as is, we create clusters out of it, smaller clusters for smaller values and larger values, larger cluster for more common values. Okay, and then we store these sort of centroids into our system, and then these centroids would represent a good would have a very similar distribution as our actual data. Okay, and our cluster size would grow like small to large and then back to small. Clear?
So this is recomputed for every batch, right? So,
this is done for every batch.
So there is no history of the previous batch that
no, it's just gone. It's just you do not have any data about that.
Okay. So
because like if you store all the data points, then it would become very costly, very costly.
Okay, so the larger memory storage you have, you can increase the batch size.
You can increase the batches if needed. Yeah.
Unit, okay.
Yeah. And obviously it depends on the amount of money you'd like to spend and amount of accuracy you're giving to your customer. So if you can bear, so you can have larger batch size, you can, because it's not only about the batch size that you are having, but also about the data points that you are raw storing in your system. If you're storing all the data points, you can store all the data points if you want, but if you're doing that, you would require a lot of space. And if you're computing on that, see, it's okay if you're storing it, but if you're even computing on that big of a data set, that would become a problem. So what you might do is you might still choose to save all the data points of a user, but you can just compute on this approximate data. Okay, so that if your user asks, I need historical data, you can just give it all the billion points. Okay, but on your interface, when you are rendering the P99 of something, you are using this approximated data.
Right.
So now that we understood what t-digest does, the challenge that comes in is like the stream of measurement that comes in. You have created a sense of cluster. When new measurements come in, right? So we have like one set of representations done. When the new measurements come in, as in the new batch of items come in, how are these clusters being updated? Okay, since we discarded other points, so problem ho jayega, because we cannot represent a cluster well. Like for example, let me take a very nice example to show you guys what the problem is. So the idea that these companies or these algorithms do is, what they do is they have a finite memory. Okay, this is a finite memory that they use, and let's say this memory has 100,000 points का space. Okay, it can store 100,000 integers value. For example, 100,000 points it can store. Okay, so now what you do is every time you have a data, okay, anytime you get a batch of data, let's say this is one batch of data, this is another batch of data, this is another batch of data, this data always gets mapped onto this memory. So all the updates of your centroid and what else, whatever your data point is, whatever you have is, so you will always represent, or you will always store, you'll always use only this much of space to store it. So the way we were discussing it up till now was like, we are just storing the centroids of the cluster in the database, right? We were discussing like that. But if you do this, if you still do this, let's say we are storing 10 points for every 1,000 points. But this means that for anytime you get 1,000 thing, you're storing 10. And now this 10 plus 10 plus 10 plus 10 plus 10, this will be continuously growing, right? So you don't want to have that much of space allocated for this approximated calculation. You might still want to store it for your raw data, but for this approximated computation, you don't want to do that. So that's why what you do is you reserve a space, and every time this batch gets computed and you store the data, you will always use this space to store it. So first data comes here, second copy comes here, third copy comes here. So first batch processed, it gets, so this is where you would store your data: 1, 2, 4, 8, something, 10, 12, 18, 20, 20, 100. Okay. And now this is what your true representation of your data is. So anytime the approximation that you will do, it will always happen on this data. Okay, let's say for first instance, you got only, I'll say finite storage. Okay, you got the first batch. This is the finite source. This is your database where you're storing the data. Okay, and in which you cannot store infinitely large amount of data. You can only store a finite representation of it. Let's say 10,000 or 20,000 points. Okay, that's what you can store, because that's when you can do fast computations on it. Okay, so let's say you have, I'll mark it as 20,000 points. So this is the max you can go to, a max 20,000 points. And this is what your database storage for a particular data point or for a particular metric is. Okay, you got the first batch, you got a batch of 1,000, you split it into clusters, and you have stored it in this system because this was empty at the first time. Okay, so this is what you stored. So these were the centroids of the clusters that you created. Now let's say you got a second batch. Let's say this was the first batch, this was the second batch. Now when the second batch came in, it also computed the clusters, and it got, like, let's say 50 more centroids. Okay, now the problem is you would want to merge these centroids into this space. Right? You cannot just simply add the values here, because it might disturb the distribution, the actual distribution combining the first and the second batch versus the distribution that you're seeing in the bottom, in this, through your approximate representation. Correct? Because these, the kind of clustering we did on first batch, the kind of clustering we did on second batch was an independent operation. So storing the centroid as is from the first batch and storing the centroid as is from the second batch in this finite space is not a good idea, because it might have an impact on your distribution. Okay, so typically what we want to do is we would want to merge this with this. Clear? Yes, no? Yes, no to throw. No? Kisko nahi samjha? Who did not get this one?
Can you please repeat up? I didn't get it.
Yeah, exactly. So obviously this sort of thing needs repetition. Batata hu. So what we did is what we want is we want a representation. So we have an actual representation and an approximate representation. Okay, what are these represented? These are representation of the actual data stream that we got. Okay, actual response time is the actual representation of it. Let's say the graph of this was like this. Okay, but it was around 1 million points. Okay, up till date. Okay, 1 million points. This is what my graph, this is what my histogram look like. Okay, and now this is my approximate representation, which is, let's say, 1,000 points. And this representation should also look like this. Very, very similar, but it should very accurately represent my data, right? So the kind of distribution this has, the kind of distribution this has should be exactly, should be very, very, very similar to each other. So that whenever I'm computing a percentile on this data, if I would have done that, versus when I'm computing percentile on this data, the output should be nearly equal. Even if it is P99, P99.9, P50, it should be very, very, very close to the actual and the approximate. Okay, the calculation on this approximate representation will be faster, because here I'm just dealing with 1,000 points. Correct. On the actual, it will suffer, because here it's 1 million points. Tomorrow it will be 2 million points, and then 1 billion points. Correct. This is the problem. How will we ensure that the representation of my the actual representation is same as my approximated representation? This is where my T-digest algorithm comes into the picture. Okay, so T-digest algorithm, what it did is, T-digest algorithm tells us that lower value and higher value requires smaller cluster sizes. So I need more accurate representation of, so basically more sampling. When you sample large amount of data, you lose out on large amount of information. Okay, when you sample small, basically, let's say out of 10, you are discarding 8 values and representing it by 2 values, versus on a sample of 100, you are discarding 98 values and just storing 2 values. Okay, so when you have a higher sampling rate, when you are sampling, basically when you're discarding a lot of information, you are basically losing out on data. So here, when the values are smaller, you would want to have smaller cluster sizes, which means more accurate representations of the data. And when the values are higher, you need more info, a very accurate representation of the data versus where it is very common. Okay, so smaller cluster size, larger cluster size, and again smaller cluster size. Okay, so this is, and now that from this approximate representation, this is what we are trying to build over here. So here we have 2000 points ka space dedicated for this metric. That's it, only 2000 points I can store at max. So now this 2000 points, this is like my approximate storage. Now, since this is my approximate storage, I would want it to be, the distribution of this should be very close to the distribution of my actual data. Okay. So when the first batch came in, which had 1000 points, out of which 10 points got sampled using this clustering algorithm, it stored the centroids in this database like this. Okay. Now, since my first time the storage was empty, approximate storage was empty, it stored it as is. Now, when my second batch came in, it applied that same algorithm, it created the clusters, it got the centroids. Now, these centroids, which it computed from the second batch, needs to be merged onto this finite storage, such that these graphs still look the same. Clear?
Yeah, so when you get the second batch, right? So it will have a different number, right? It's not the same number.
Exactly.
So
Exactly. It will have a different number, but that's where the challenge is, where the kind of, because this sort of, these centroids will be created on this data, right? But what would we want is, we want when this centroids are merged with this centroids and stored on this location, the graph representation or the distribution of the data should be very same from the actual representation and the approximate representation.
So
right,
just
this is
question. So
Hmm.
can you go a little top? So we have divided it two batches. So first and second one. So as you mentioned, we'll be sorting the inputs.
Sorting the data within this batch.
Okay, within that batch, not the whole.
Because once the batch is done, utna hi store ho gaya, baaki sab discard ho gaya na.
Okay. So second batch is the next day data, not the
second is
actual.
Exactly, second batch is the next data that came in.
Okay.
Right, so that's where you would have to have like these centroids and these data points getting merged so that the representations remains fairly same. Yeah, this is where the challenge is. Or yahan pe, so basically T-Digest recommends ki how would you sample the data so that it represents the actual representation. This is where T-Digest got over, ki khatam ho gaya uska kaam, and yahan pe this part comes in, where your job is to like merge this data. Okay, so how do you do that? So this is where the representation that we talked about, the centroid, but for how many points comes into the picture. So what do we do is, what do we store is, we store the centroid, the weight. The weight is the number of points in a cluster. So let's say the cluster of 5, we chose 1 point. So the weight is the number of points in the cluster. Let's say the cluster was of, so the number of points in the cluster were 100, out of which we chose 1 centroid, which was that one value. Let's say 55 was that value. Okay, so 55, 100. Okay, and what's the cost? Cost is the sum of the distances from the member points to the centroid. So for each of the member of the centroid, of the cluster, what's its distance from what's its distance from the centroid, and the summation of this would be the cost of this cluster. Okay, these are the 3 things that we use to while merging it. So we would have the centroid, which is the actual centroid of this of the cluster. We would have the weight, which is the total number of points in the cluster. So basically, when you multiply a centroid by the, so if the centroid was the mean, so mean into the number of points of the cluster would give you the total weight. Wala maths ka problem. It's very similar to that. So centroid is the actual centroid that was stored in the that came out of that batch. The weight is the total number of points in the cluster, and the cost is the sum of distance of from the member points to the centroid. And now when we merge the two clusters, the data that we store, so the data that will store over here would be the centroid. So when the clusters are merged, let's say you have two data points which are very near to each other, and you say, okay, now these two, because you got the first batch and you stored it over here, you got the second batch. Now you can apply a very similar logic of clustering and merging as we did before on this data, so that you get a very accurate representation of it. So this is basically doing a similar t-digest operation here as well, where what you do is you do a weighted, so the centroid, when your two clusters are about to be merged, okay, you can have a criteria around this. Two clusters, if the centroids are too closer to each other, then this cluster needs to be merged. This is again given by a formula. Okay, this is part of the research paper as well. So when the two clusters are to be merged, the idea is the new centroid is the weighted average of the centroids of the cluster that are to be merged. Let's say two clusters are merged, is the weighted average of the centroids. The total weight of this new cluster will be equal to the summation of weights of the two centroids, and the total cost of the new cluster will be equal to weight multiplied by the distance from the centroid to the new centroid. So because other data points are deleted, are discarded, you only have the centroids, the weight and the cost information for what it is represented. And then you would do the summation of all the clusters that are merging. So if two clusters are merging, you would do the sum of product of the weight of the individual clusters multiplied by the cost of it, which is the distance from the centroid to the new centroid. So the new centroid and the old centroid ke beech ka distance. So this is the new cost, the new weight, and the new centroid. So this way, without overspilling this finite memory, we can keep on merging the old data and the new data in this space, which continues to represent, or which continues to have the same representation as the actual data. Okay, this is what this algorithm is all about. So cluster merging and doing this. So you would constantly keep on merging the clusters. You would constantly find out computing the clusters, and by using a finite memory, right? So this is not like with time, this would not grow. And this is for an approximate computation, not actual computation. Actual computation might take a lot of time. You might store the actual data, actual raw points as is. But this is all about storing approximate, or doing quick computations on the fly for the users to give them like faster dashboards, but with very less error rate. Right, so having a finite memory, you would have to keep on merging it, and that's where you would apply this merging wala logic. Yeah, this is all about t-digest, and this is exactly what New Relic and Datadog does. I found this thing in their blog and went through it, and they wrote exactly this thing. This is what they do. It's very easy to build this, write this in Python. Hardly takes a day for you to implement this. And obviously go through t-digest paper to find out that formula that gives you how big your cluster should be, what's the min and max value of cluster, basically what's the threshold after which you create a new cluster, because this is where the challenge comes in. वो green wala tha na apna, this wala, कि when my first cluster ends and when my second cluster starts, how will you identify that? This is where that seemingly complicated mathematical equation comes into the picture. But this is what the algorithm is and how these guys are doing it at scale. So any metric that you see on your Datadog or your New Relic, all the computations that you see happen on this finite storage, on this approximate data. It is not happening on the actual representation of it, because actual representation may have billions of points. So billions of points per percentile nikalna, it takes a lot of time to do that. That's where they use this approximate representation, and they ensure that this approximate representation is very close to our actual representation by using t-digest, so that it does not vary. It does not vary from the actual histogrammic representation of your data.
And this is how you build Neuralink, Datadog, और इनका सबसे बड़ा challenging part. Ingestion, scaling, building, sharding, wording is all okay. This is where the magic lies. Yeah, and this is all about T-Digest. Any questions? Right? अरे वाह, सही है. चलो. In case you guys have any other questions, feel free to like ping me. Don't hesitate. And this basically concludes all the topics, all the questions that I wanted to cover. As part of conclusion, what I also want to add is, what else to read. A few things that I would definitely want you to cover from the algorithmic side, especially, is probabilistic counters. This is very important. Operational transformation, differential synchronization for collaborative editing. This is the algorithm that runs Google Docs or any collaborative software. Then count min sketches, we did utter about it yesterday. Hyperlog we already covered, but the algorithm of it using Flageolet Martin, do that. Convex hull, very simple algorithm, but very effective. Find that. So basically convex hull says that so basically given a bunch of points, what's the outermost boundary of this thing? So it basically tries to create a convex polygon given all the points. Basically which basically encloses all the points. That's what it does. A convex hull. A very simple but a very effective algorithm. And quad and Merkle trees. Just if you'd want to. So it's more towards the S2 geometry and the geolocation side of things. Quad trees and Merkle trees, you can do that. Merkle trees are also using Git to some extent, and quad trees you can obviously for the data or for the geolocation side of things. And yeah, this concludes everything that I wanted to cover. So, any question, guys?
Arpit, you mentioned about the event-driven system course that you are planning to bring. So कुछ उसका वो कब आ रहा है?
अभी तो चालू किया है मैंने बनाना. मैं तो बहुत रिसर्च कर रहा हूँ उस पे. I spend a month already, but mostly 1-1.5 महीने की रिसर्च करूंगा उस पे मैं एकदम पूरा end to end, because it has to be, मतलब it will be a very short course, but a very again dense और सब कुछ cover करना है. So right from how industry uses it, going through all the blogs and all, I'm doing a lot of extensive research. So I got a chance to build one for Unacademy very recently. So I thought कि चलो course भी बना देते इसके ऊपर. That's how it started. तो production में जो issues आते हैं, I've started jotting them down, trying basically formal analysis of it, so that I can add as much value from the real system as I can. तो थोड़ा सा time लगेगा, maybe a month or two, to at least basically finalize the content. I'll obviously skim the content with you guys. If you guys find it helpful, then I'll start filming it. Mostly it will be recorded and not a cohort based course, because not a lot of people might want to enroll in it. That's fine.
Okay.
Nice. चलो.
But इस कोर्स में काफी मजा आया यार अर्पित. मतलब हमें वीडियोस कई बार देखना पड़ता है.
वो देखना पड़ेगा, वो तो है.
But it was
intense है, but हाँ, I just tried to cover as much breadth as I could. Again, except a couple of algorithms or a couple of systems, बाकी सारे पे directly or indirectly I've basically fortunate enough to got a chance to work on it. तो काफी मेरे को भी मजा आ रहा था पढ़ाने में. But there are so many things that I can talk about. Like and basically for this batch especially, there are 6 questions that I've never ever talked about before कभी भी. तो मेरे को बहुत मजा आया नई चीजें कवर करने में. लाइक एडटेक वाला, कल इंप्रेशंस वाला तो एकदम ही नया था. बट हाँ, थैंक्स अंकुर फॉर द काइंड वर्ड्स. मुझे बड़ा मजा आया. दिस बैच वाज अ लिटिल वियर्ड फ्रॉम अदर बैचेस, बट इट वाज अ गुड वियर्ड, नॉट अ बैड वियर्ड. बट हाँ, इट वाज फन.
Arpit, like if you discuss any new problems in the coming classes,
yeah, मेरे को भी चाहिए.
Like, do we get notified about the new design which you have?
See, the thing is like code based course पे पूरा class में discussion चलता है. Like for example, medium class I never discussed before. वो class पे whatever question comes up, it comes up, right? वो कभी discuss होता है, and obviously I cannot like snip that much of part because it has lot of before and after ka context. So I'm still planning to, you know, once I discard a system, basically once I discard a system from my cohort, I can just create a separate recorded video out of it, not the actual cohort video, but a separate detailed video out of it and just post it somehow. I'm planning that, but अब थोड़ा time निकालना थोड़ा हो रहा है मेरा, because you know वही marketing and sales run करना पड़ता है and content creation, क्योंकि लोग enroll नहीं करते, वो सब करना पड़ता है. So once I get some time, some breathing space around it, I have that in my roadmap.
And one more on the hyperlog log, which you mentioned last class.
Hmm.
I just looked into the blog. So it's more specific to a number. So if you try to implement the same with user ID,
a number.
Yeah, so you took the string of the numbers and try to set a build.
Got it.
So like how to actually implement for user ID? It's a string. We can't match it with a number.
No. So but string ka number representation can be done, na?
ASCII representation.
Okay.
Because at the end, what it does is it just matches the zeros of it that basically comes in, right? So you can apply, it might be lossy, but you can actually change the string to a number, right? So some straightforward conversion of it. Maybe it is an hexadecimal string. So you can just convert it to an integer, maybe with some lossiness. कि आगे के कुछ digits नहीं आएंगे. If it is in Python, then it's still no problem for you.
But do you have a numbering for the user?
Mostly user IDs are integers, but still, if it's a UUID sort of stuff, then you might have to do some transformation on it. मैंने देखा नहीं actually, अच्छा point है. I should explore more on this. I've never seen that. Sorry. मैं देखता हूँ उसके ऊपर definitely. Made a note of it.
Arvind, can you suggest any resources or blogs for newsfeed generation? That kind of a problem. Building like a Twitter news, things like
It's a very common statement, sir. Newsfeed wala part mein, it's all about like bringing in sources from like multiple, bringing in data from multiple sources. It's all about that.
Right. So that we run into the very common problem of doing a cross-shard join, right? So
you can never do a cross-shard join. वो तो problem है. You cannot do that. So that's where you would have to have an event-driven system somehow. And basically that's what you do in order to generate that. I can just spend 5 minutes talking about that. So the way you can generate a feed. So यहाँ पे there are two parts of it. So cross-shard join is not possible. So that's where every single event, every single new post which is published, what you do is you might have a system that reads this event and sees key out of these, to which of the followers के feed में I should inject this post. Correct. So all the loyal followers के feed में it gets injected. So something like you might have for every user you might have a loyal follower की list. Okay, and for them it gets injected in that feed. Okay. Then second one is recommendation. So whom should I recommend this part? So if a user makes a post, then the recommendation algorithm kicks in, and basically there would be what? There would be like a feed ka array for every user, right? And from that, depending on what a user is watching, you can pick what is recommended and just inject it in their feed, similar to what TikTok or Insta Reel or LinkedIn does. Right. Okay. Doing a cross-shard join for just finding that very close thing. Ki, my friends are doing this. I want every update from them. But that's why all of these platforms have this either notification bell icon sort of stuff, or they ask you to mark them as close friends. So this is that indication that whenever I'm publishing something, I want to definitely send it to them. Otherwise, everything is driven from the recommendation system.
Right, because for celebrity like accounts, you'll have million followers, so then you have to do a lot of writes.
Correct. So in that case, you never push it into the feed. Rather, the feed may, what happens is there are two mechanisms. One is push and one is pull. So for a celebrity account, they pull if the celebrity has posted recently or not, and it first pulls it up, and then and for other it is push based. So when my friend posted something, it is pushed into my feed. But when my feed is loaded, it makes one more call that goes to a celebrity account and sees that the celebrity accounts that I follow, have they posted something? Because a high right fan out for celebrity accounts is not possible. It's a very common pattern. A lot of people have talked about it. A lot of literature already available on that. And even when I was building a feed for Unacademy, me and 5 other folks, we built something very similar. We had a couple of educators having millions of having at that time hundreds and thousands of followers. So we didn't fan out. We made 2 API calls when our feed loaded. One that fetches feed from that person, and second that makes another call to all the celebrity account that the user follows and sees if they made something new post, and then it pulls and this thing.
Okay. And if we're kind of rewatching these videos and you have doubts, can we reach out on the Discord?
Yeah, anytime you can any time reach out. Perfectly fine. And obviously this was dense. You might have to go through it twice or thrice. That's perfectly fine. And obviously that's how it should be. It should, if I'm taking a course in which I just teach it once and you get it and you understand it, that's of no use. Which means that course was not good enough. It should make you think, yeah, I have to rewatch it, because that's when it becomes like fun, interesting, challenging, and it basically covers that depth. Push lena, don't no worries, sir. Anytime feel free to reach out.
Okay.
Yeah, nice. Amazing. Thanks a ton, guys. It was fun 2 months for me. Got to learn a lot of stuff with the help of you guys. A lot of concepts got cleared in my head as well. I tried to cover new things in this cohort. I'll continue to take those, but point taken. I'll try to, segregate the process. If I cover anything new, I'll try to, compile a separate video and put it out so that it helps others. That's what my plan is. I'm just a little stuck with my content creation just because I get people enrolled into course. Now I'm just with my newsletter and stuff. A little bogged down, but I'm still definitely working on that. I have those things in mind for sure. But any which ways, thanks a ton for being part of this course. I thoroughly enjoyed it, and I hope if I create new course, I'd see some of you joining it. I really wish that, but I'll just keep you guys posted. And anyway, I have Relog now, in which I can build anything that I want. It's a free playground for me right now. So I'll build a lot of interesting things, planning courses. Everything will be hosted there. All the communications will happen through that only. वहाँ पे ही सब आएगा. So planning to create a global repository of resources sort of stuff, and also in progress is a curated course on system design that I'll give all of you guys access to. उस पे भी चालू है, but it requires a lot of research from my end. I'm just pulling that in. So a lot of work in progress for me definitely right now. करो एक करके complete करता हूँ वो सब मैं. But a lot of things are planned. A lot of interesting things are planned. Amazing,
yeah.
amazing.
Thanks, Arvind. It was really nice, and we'll miss actually weekend discussion at least, right? 4 to 6 wala.
Yeah, I don't know. I'd miss too. Finally, I have one weekend off next weekend. मजा आ गया, but anyways, feel free to reach out, guys. I'm always there for a quick chat. Soon I'll plan something interesting for you guys. Hi guys. Chala.
Thanks,
Amazing.
Arpit. That was great.
Thanks.
Great experience.
Thanks,
Thank
Arpit.
you.
Sure.
Thanks,
Arpit.
Sarthak, Rahul.
Great
Vishal.
course.
Thanks, Chandan.
Thanks,
Chala.
Arpit.
Bye bye, guys. Stay safe.
Bye.
Bye.
Thanks.
Bye.
Bye bye.